solutions, you have room to be more efficient. Again, efficiency is, it's a key here because many of the solutions are much longer and the method is not the most efficient method. So even if you got the full credit on any problem, please look at my solution, study my solution, and compare. All right. The more methods you know, the better it is. So don't be afraid to study more different methods. Okay, so why don't we look at the first problem here? Number one problem: find the cubic polynomial. Find the cubic polynomial with the inflection point at 2,1 and relative maximum at 0,5. So because we have this information about this inflection point 2 at 2,1, that means the second derivative is actually 0. And therefore, we can actually start from the second derivative f. F double prime is going to be x minus 2 times a times x minus 2. And we know that x equals 2 must be a 0 of second derivative and must be a single root. And this is a cubic polynomial. The second derivative must be a linear function. And therefore, the second derivative can only be a times something a minus 2. Does everybody get this? Does everybody get that the f double prime has to be this guy right here? Oh, by the way, I think most of you started with this. Most of you started with a is equal to ax cubed, and then what? Plus bx squared, and then plus cx plus d. And in this case, even if you do it this way, the c and the d comes out really quickly. The d is equal to 5 and c is equal to 0. So there's really not much. It's not too bad. But the way I present it right here, I think is more efficient. Okay, it's definitely more efficient. Doesn't it look shorter, by the way? Okay, so f double prime of x is equal to a times x minus 2. Anybody has a question right here? Anybody has a question there? Okay, how about this? Since I don't have any response here, does anybody have any questions? Does any of you want me to go over any questions from the test? I think it's useless for me to just go over everything unless you have any questions. You just look up the answer key. Does anybody have any questions on any questions on the test? Then I will just go over those questions.
Could you go over number 4?
Number 4, sure. So let me just, what is it? Oh, I didn't have to save any of this. Okay, clear. So let me just clear this. Number 4. Oh, yeah, number 4. Yeah, I like number 4 because number 4 is, like I said, is still a short problem. Now here, I would like to, before I get into this here, let me make some general, some more specific general comments. Is this? The comment is about the notation. It's about the notation. G prime of x means that this one is clear. This is equal to d dx of g of x. But the confusion comes when we have d prime of, we have this right here. This is clear. But the question is, so what is then g prime of 2x? So g prime of 2x, let me tell you, the question is, this is equal to, this is equal to, this is equal to, this is not d dx of, not d dx of, again, this is not d dx of g prime of x. This is a bit confusing. D prime of 2x is not d dx of gx. What g prime of x is this? What is this g prime of 2x? So that's why on this test, on this problem, I did not write this prime notation just to make sure that I did not create any confusion. This right here is actually equal to d of the derivative of ddx, not ddx, but dd2x of g of 2x. I know this sounds weird, but there's a danger here. And that's because it's this right here. This is correct. That's because when you write this g prime here, this g prime is really ddx of g of x. So this guy and this guy must match. It's like this. If I say let's say h prime of 2x, h prime of 2x, what is h prime of 2x? Is h prime equal to ddx of h of 2x? Now the question is that correct? Is this equal to h of x? H of 2x, that is. The question is this correct? You know, everybody, the last statement I wrote down right here, is this correct? Question mark. What do you think? H prime of 2x is actually this. D of 2x and h of 2x. This is the correct one. So therefore, the top one is actually is incorrect. So this one right here, incorrect. Okay, so let me write this down. Let me write incorrect. But on this problem, I wrote it clearly. I wrote ddx. I wrote ddx here. I did not write I did not write g prime of x, because that would create a confusion. Okay, so now class, let me just go over example 4 now. Now we are ready. Okay. Okay, so example 4. The question was this. The question was let me write this down. The question was evaluate this guy right here. That was the question, right? Okay, so, well, what is g of 2x? G of 2x is this guy right here. And then we have g of 8x plus 3, which is right here. And then plus g of 4x plus 1 is right here. The first thing you can notice that, look at this guy. You see this 8x plus 3 and 8x plus 3 right here. And do you see that 4x plus 1 right here is this one right here? So the sum of the three intervals becomes this guy right here. And so the question actually becomes this one problem right here. And this is something where a lot of you missed. I think you have to be a little more careful when you look at when you do these problems here. Okay. So once you combine the three intervals, then you have one time interval. You only have that. And then we have done enough of this. Well, did you do many of this? You know, I didn't. I don't think I did too many of this, but I did make a mention of this. We spent quite some time. So we have a variable on the upper limit and the lower limit. We split this. So why don't we split this at 0? You can split this up at any point. So we take the interval from 0 to 16x plus 7, and then minus the interval from 0 to 2x. It should be really from 2x is 0 plus 2x is 0 to 16x plus 7. So we subtract this, apply the negative property of definite intervals, and then you get that. And then what? And then this is how you write it. And then apply the chain rule, and then the final answer comes out with this right here. So problem number 4, just like all the other problems, are actually quite short. Again, all the problems up to problem number 6 is actually quite short. I would not say it's easy, but they are quite short. All of them can literally be done in about 5 minutes. with the exception of problem number 7. Problem number 7 is the Riemann sum. So it would take, I don't know, maybe up to 10 minutes. But that's the only one which would take more than 5 minutes. All the other problems, if you just do it carefully and efficiently, then it does not take, none of the problems really take more than 5 minutes. Yeah, question on problem number 4. Any questions here? Any questions on number 4, class?
Could you go over 5 as well?
The 5 is right underneath it. Yeah, so right here. So this one here, by the way, this here, when you look at this answer right here, it kind of looks scary. It looks difficult. But actually, we have done many of these things. You know the example we did? One of the examples we did was this. Let's say integral of, and the integral where we have what? Cosine of, let's have what? How about cosine of square of x? And then over what? Square of x dx. I think one of the problems we had on the section was this right here. And so in this case, what we do is we let, and by the way, I think I forgot to tell you, the most common substitution letter is U. I think I should have mentioned this before. The whole world uses U. I think U is a very common letter. So sometimes this section on substitution, they actually call it U substitution, because the letter U is actually the most common letter. Although I like to use the letter W, but W I cannot use here because W is already used. So can I use W? So in this case, let me use U. So in this case, if you look at this here, note that if you substitute something for square root of x, then this square root of x in the denominator is kind of waiting here, because if U is equal to square root of x, then the question is, what is du? Well, du comes out to be what? The derivative of x to half power is half x to the negative half power. So we get 2 square root of x, and then dx. So this is what we get. So the derivative of square root of x is x to the minus half, which is this right here, except for the constant. So that's the hint. So now here, if you look at this from here, well, what do we see? We see this guy here. Note that we have a f of x, f of t here, but then this is under the square root. So what that means is we actually have a square root of f of t in the bottom. So this is the hint. Is this the hint? Then what that means is this thing is happening here. So in this case, what do? We just let u to be square root of x. That's what we need. So in this case, and for that problem, now for this one, what do? Let u is equal to square root of u plus w. By the way, this w is not a variable. This w is a number. So this one, again, this w is actually a number. Okay, so this is not a variable. This is not this w is a number. I said w is what? It's the last digit of your SNC ID. So whatever that is, this w is a number. So in this case, I am changing from t to u. If u is equal to square root of f of t plus square root of f of t plus w, which is right here, I'm going to let this whole thing be u. What happens here? Then du turns out to be this right here. So if du is that, then du is this. So the derivative of square root of f of t plus w with respect to t, what is that? That will be half times f of t to the minus half power, and in times the derivative of f of t, which is f prime of t, chain rule. So now, what is this guy right here? This guy right here is equal to what? This guy right here is a part which I marked in red. It's actually right here. That's right here. And that guy right there becomes what? Becomes 2du. And then this part right here, and then this part right here becomes what? Becomes square root of u. Right here. So initially, the initial integral looks very messy, but it kind of looks messy. It is not really that messy as you think. Okay, so in the active substitution here, you get this integral right here. You get a very nice integral, and then the limits will change, of course, too. The upper limit and the lower limit, we have to change from t to u. So when t equals 1, then u is equal to the square root of f of 1 plus w. And then the upper limit, when t is equal to 4, that will equal u is equal to the square root of f of 4 plus w. So yeah, you change the upper limit and the lower limit, but you get this. And then when you integrate, you get that. And then all you have to do is what? Evaluate that right there. And then that's it. So maybe I'll clear this. Just to bring down scroll this now, and then that's it. See? Number 5. Number 5 is really not so hard. Well, it is easy. It's not easy because you have to know the substitution, but you have seen this pattern here. So the key thing to note is that there is a square root of 2 here. The key thing to note is that there is the square root of f of t over here. That's the key thing to note. So when you have a square root of f of t in the bottom here, what is it? What is the substitution here? That means the substitution should be u is equal to square root of f of t. That's basically you get the idea from here, and so you must get this because the square root of because the derivative of square root of x is 1 over 2 times square root of x. So that's the key. So once again, what is the derivative of square root of x? The square root of the derivative of the square root of x is equal to what? Is equal to 2 square root of x and then 1 here. So the key is that when you take the derivative of the square root of x, you get this square root of x in the bottom. And again, when you look at this from here, you see this f of t right here, which you see right here. That's the hint. That means the u is equal to square root of f of t. And then if you look at this guy, there's also a plus w there. So you may or may not include that plus w, but if you include that plus w into that substitution, then it's actually easier. But even if you do not put that w, it still works. But this is the best substitution right here. And once you make that substitution, then going through all this, you get this, and then you make a substitution. That's it. But it is not really meant to be such a complicated problem. Now, many of you did 2 steps. What you did was you did u is equal to, let's say you did u is equal to, and then you did f of x, f of t. You did not f of t. That's right, f of t. You did u is equal to f of t, and then after that, what you did was that you did v is equal to square root of u. You did this in 2 steps, and if you did this in 2 steps, does it work? Yes, it does. Okay. If you do this in 2 steps, so this right here, many of you did this in 2 steps, and that's good. Okay, it's not bad. But the one I showed you is in 1 step. U is equal to square root of f of t. That's in 1 step. Okay, so it's actually easier. I don't know. What's this number 5 too tricky? It's tricky. Do you think this number 5 problem was too tricky? I think the tricky part is that there's an f of t there, but other than that, it's actually So anyway, it's something very standard. It is not easy, but it is not something unusual. Okay, we have done this kind of square root substitution, a few times. So we even did a substitution on cube root of w, a cube root of x. At least this is not cube root of x. This is square root of x. So we have done a few times on this kind of thing. So anyway, you look at the pattern here, and so you see the square root of f of t. That means that's a hint that you should be square root of f of t. So its derivative is this guy right here. Okay? Any questions on number 5? Any questions on any other problems? Okay, by the way, on problem number 7, which I didn't do, the problem number 7, you had to evaluate this integral by Riemann sum. By Riemann sum, that is by that limit sigma, that limit and then that sigma. And then many of you didn't read the instruction carefully. Again, if I look at the instruction here, let me see. Let me just read the instruction. It says here, I did say, evaluate the following definite integral according to the limit sigma definition of definite integral. And I underlined that too. Again, limit sigma definition of definite integral. I cannot make it any more clear than this. Again, limit sigma definition of definite integral, or even, whenever you see the word definition, again, whenever you see the definition, pay close attention, because it means that you must use a definition. And in addition to that, I said, do not apply FTC. Do not apply FTC either part 1 or part 2. Do not apply FTC. So FTC, you cannot apply here. Maybe you know what this FTC is, but you cannot evaluate this definite integral just by finding an antiderivative and then plugging in the value. That's the FTC. That's FTC part 2. So we have FTC part 1 and part 2. Here, I specifically said not to use FTC. And I did say, according to the limit sigma definition of definite integral, I cannot really make it more clear than this. I even underlined it too. Yes, many of you, I don't know, didn't read the question carefully and just started to just apply the fundamental theorem calculus, use integral x squared to 1/3 x cubed. You know what? This is a very simple problem. See, do you see this number 7? Why would I give you a problem such as that? Do you think I would give a problem like this? I would integrate from -1 to 2, and then integrate this from what? X squared minus 2x? Do you think that would be a good idea? Do you think I would give this on problem number 7? This right here? I think this is a little bit too much. Don't you think so? Do you think this was a problem? Just using the fundamental theorem calculus? Or class? Excuse me? Just give me 1 minute. I'll be back in 1 minute, okay? Excuse me, I'm back here. Okay, does anybody have any questions on any of the questions on the test? Any of these questions was unfairly difficult? What do you think? Were any of these questions unfairly difficult?
Could we go over question 2?
Question 2?
Yep.
Okay, all right, question 2. All right. So let me erase all this. Let's go to question 2. The question 2 has 3 parts, but all 3 parts are actually quite manageable. So let's look at question 2, part A. I don't know. I think some of you did not even get part A, so that was a difficult. Yeah, I guess it's not an easy problem. Okay, so what is this? The problem of the first part 2A. did you have any specific question within problem 2, or did you want me to just go over all 3 parts?
In the question it said that the function they gave, that was a condition. It didn't say that that was the function that we needed to work with.
Huh?
In the question, the
Yeah.
f, it said that that's a condition.
Yeah, that's a condition. So we have given a function. So this f of x function right here is not given, but this is a function which has this property. So we don't know what this function is, but what we do know about this function is that it has this property right here. The property that the integral from r to r plus 1 of f of x dx is equal to r squared for every r, not for some r, but for every r. So here, function f is not given, but a property of function f is given. And on this problem, that's all you need. You don't need to know what the function is, because we have a property of this function, and that is all you need on all 3 parts of it. So if you look at the problem number part A, the part A is this right here, and then plus this right here. So note that there's a gap between 1 to 2. So what we do is, from here what we do is, we add integral from 1 to 2, and then we subtract integral from 1 to 2. So if we add the integral of f from 1 to 2, and then we subtract the integral from 1 to 2, then what happens is, once we add the integral of f from 1 to 2, then we get from 0.3 to 1, and then 1 to 2, and then 2 to 2.3. So we get this guy here. So we get integral of f from 0.3 to 2.3, and then we get to subtract the integral from 1 to 2. I don't know, does everybody get the first step? Tell me if anything is not clear.
Yeah, no, I get it now.
Because as you can see, this is from 0.3 to 1, and then from 2 to 2.3, so we can see that there's a gap from 1 to 2. So to fit in the gap, what we do is, we add the integral of f from 1 to 2, and then we subtract the integral of f from 1 to 2. So if we add and subtract it, then what happens is, we now end up getting the integral from 0.3 to 1, and then 1 to 2, and then from 2 to 2.3. So when you add up those 3 integrals, we end up getting this. And then we have to subtract this guy. So that would be the first step. And now the question is, how do we compute this integral of f from 0.3 to 2.3? Well, that is obviously this integral from 0.3 to 2.3. Well, this one is not too hard. This is going to be simply this is what is f. This is equal to the integral of f from what? This is the integral of f from 0.1, 0.3 to 1.3, and then plus the integral of f from 1.3 till 2.3. And now this is from 1.3 to 2.3, and this from 0.3 to 1.3, and now we are ready to use this property. Now we go to the property where it says here, if you have integral of f from r to r plus 1, note that it's r to r plus 1. The upper limit must be exactly 1 more than the lower limit. That's what we have right here. And so that comes out to be 0.3 squared, and then plus 1.3 squared. And then we subtract that math integral from 1 to 2, which is 1 squared. And then there we go, that's the answer right there. So was that too tricky? Was that too tricky?
What threw me off with this one were the decimals, because I thought I remember you saying we don't do decimals in this class.
Yeah, you can do fractions if you like. What I did was here, what is not allowed is this. What is not allowed is not decimals, but approximate decimals are not allowed.
Oh, right.
Approximate decimals. Approximated decimals are not allowed. are not allowed. So basically, let's say if you solve a problem and you get into a and then you get into a number like 1/7, like 1/7, then this kind of fraction should never be converted to decimal. Why? Because this guy 1/7. It's not the most lovely fractions. By the way, this is a repeating decimal, 0.142857, and then this guy is 6 digits repeating. It is a 6-digit repeating decimal. So the reason why I am stressing also for those of you who are using calculators or graphing calculators or graphing utilities, although these days, the decimals.com is very smart, they actually give you the answer in fractions. But if you're not using decimals, if you're using a calculator or something, still many calculators or graphing calculators, by the way, even in decimals, if you look at the graph and look for the intersection, they give all the intersection in decimals. So those decimals are not allowed, or not just for 1/7. But let's say, for example, like what? For example, like a square root of 2. So what is this here? Let's say when you get into a number like square root of 2 or pi or any of this here, they should be written that way. You just keep writing that, but you don't convert these into decimals. But in this case, you have a decimal like 0.3. Nothing wrong with this. Or if you just use fractions if you thought that way. But whether you use 0.3 or 3/10, either way, it's the same thing. In fact, many of you did give me the answer in fractions. But again, that's okay. But what I'm saying is, when you get into numbers like 1/7 or square root of 2, or let's say pi, or let's say you get into how about sine of? What is sine of? Let's say 60 degrees. These guys. If you convert them into decimals, that will be a mistake. So what is sine 60? Sine 60 is square root of 3/2. But you are not going to convert this to decimals. In decimal, that would be about 0.866. But that's an approximation. So that is not allowed. Any kind of approximated decimals are not allowed. All right? Is that clear? But if I try to explain this too much here, then you know what? Students get mixed up. And so just to make it clearly, if I tell the students decimals are allowed, but approximate decimals are allowed, you know what the students think? The students think that, so decimals are allowed. And then they start using approximate decimals all over the place. So I have to make this over clear. To make this over clear, so that the students will have no room to misunderstand, I am stressing don't use decimals. Okay, is that clear? But the fact is, approximate decimals are not allowed. Basically, if you're using a calculator or any kind of graphing utility or calculator or any of that type, then they give the answer in decimal, and they are not allowed. Approximated numbers are not allowed. That's what I'm saying here. Basically, approximates are not allowed. That's what I mean. If you approximate number, that will be not acceptable here, not in this class. But to stress this, and I have to make it very clear, so I have to say, decimals are not allowed. But the fact is, approximate decimals are allowed. But you know what? To make it clear, to make it very clear, is difficult. The students don't listen to all the details. So that's why if I tell them decimals are allowed, but decimals not allowed, then decimals are allowed, decimals are allowed. And so they start using decimals all over the place. And that is not what I want to happen. Okay? That is not what I want it to happen. So therefore, here I'm telling you, here like 0.3, 1.3, no problem. Again, if you use fraction, that's okay too. But exact decimals which are not approximated, they are okay. All right? So anyway, so the question is from part 2 is basically, did you go from here? So here, let me clear this. Did you go from here to here? Once you come to this right here, then basically, for those of you who got up to here, of course, you do get the final answer. The rest of it is very easily understood. So going from here to here, the first step, that would be the problem. Okay? Again, in this case, function f of x is an unknown function. but this is a property of the function. By the way, there's a way to find what this f of x is. Okay, so I don't know. After this class over, why don't you try to figure out what this f of x really is? There's a way to actually find this f of x. Okay, but I'm not going to do that for you. Okay, but there's a way to find the f of x, and we have all the skills needed to find that f of x in this class. Again, to find that f of x, we have all the skills we need in this course. We have already covered it already. And that was chapter 4. The fundamental theorem of calculus. We have done all that, and so there's a way to get that f of x. Okay? All right, so that was 2a. And then 2b, when you look at the solution, it looks very, very confusing because I did the general version of putting this v plus 7. But if you can just give me one particular v, then this whole thing looks so much easier. So this is a general case. Okay, so anyway, the answer comes out with this guy right here, depending on what your v is. And many of you did this correctly. But you have to understand this property very carefully. You know this property right here? You have to understand this property really well and know how to use that property. So this all the problem, all parts A, B, C, they are around. They are written around the key. Basically, this is the key information in all three of them. Okay. Any more questions on part B or part C? And by the way, class, for part C, let me make some comment. So the integral of f from c to c plus 3, and then you get this. I think almost everybody got this up to here, and then when you multiply that, you get this. Now almost everybody got up to here, and then the question is from here, how do you show that this is 2 or greater? And then all you had to do was completing square. Completing square. Completing square is 1,000 times more important than what? Than quadratic formula. How many times do I have to say this? Completing square is 1,000 times more important than quadratic formula, in case nobody told you. Because in school, I think they stress this quadratic formula so much. Unfortunately, students learn the quadratic formula. By the way, the quadratic formula is proven by completing square, in case you didn't know. The quadratic formula is proven by what? By completing square. Yes, the students learn everything about the quadratic formula and don't know the completing square. By the way, this quadratic equation and quadratic function, quadratic expression, all of these things here, do you think they will disappear after this course? You know, this quadratic expression, quadratic function, the quadratic equation. All this. So whenever you're dealing with quadratic expression, quadratic function, quadratic equation, you know what you need? Need what? What do you need? Need what? Completing square. I think I did mention this completing square a long time ago, didn't I? Did I mention completing square of 22 years ago in our class? What do you think? I did. That if you know completing square, then you don't need quadratic formula. Okay? And so from here, so let me talk about, so this right here, from here, what is that equal to? That basically, I kind of skipped a step here. 3 times we get c squared, and then we get plus 2c. And the complete square in this case is so easy, because the numbers are very easy. And and then all you have to is the plus 5 at the end. And then what is the term which we need to complete the square? Well, c squared plus 2x, 2c, so we have 1c here, 1c. So take this number 2, multiply that by half, and then square. So the number we really need is plus 1 and minus 1. That's what I call the magic number. And then when you do that, then c squared plus 2c plus 1 becomes c plus 1 squared. And then there's a 3 here. And then 3 times minus 1 is minus 3 in the plus 5. That makes it plus 2. And by the way, once you write this in complete square form, you don't have to say anything. Oh, you know what? I made a mistake. This is actually greater than 2. Should have written greater than 2, because this guy right here is 3 times something square, should always be positive. We assume that the c is a real number. So we assume that c is a real number. So 3 times something square, and then so that's positive, and then plus 2, so that is greater than 2. And that's it. See? Isn't that simple? By the way, this one here, you don't even need calculus. You don't need calculus. And don't memorize this, is minus a over 2b. And then some of you are using that formula, the 2b, or some of you are using that a over, the b squared minus 4ac. You know what? The 4ac over c over a. You know what? All of these things, you know what? You're memorizing too much. And again, for those of you who are using that or using that right there, I don't want to say it's wrong. It's not wrong, but you have too many things to memorize. And you know what? This is hard to explain. It's not clear. These are what I call unclear methods. You are doing things in the back stage. You don't know what's happening in the front stage. But if you do complete square here, this is it. There's nothing more to it. You don't need the quadratic formula. You don't need any explanation. There's nothing to explain. So do you see this? So let me tell you this one more time. Completing square is 1,000 times more important than the quadratic formula. And this is actually covered in intermediate algebra. This is already way beyond our course. But this quadratic stuff is going to show up in every math course you take. Again, this quadratic whatever will show up again and again in all the math courses you will be taking. So this completing square, do you think it's over? No. Completing square, we are using our class, this is Calc 1, but completing square will not disappear. Does not go away. So it is not too late that you do master completing square. So let me tell you this one more time here before it's too late. Let me tell you, what is this here? Master what? Master, let me write here. What is this here? Here, master completing square. I guess this is hard, yeah? I think mastering the completing square right now is very tough, right? So I'm trying to train an old stuff, right? I think all of you already know. All of you know how to deal with algebra, and so if you have not been applying completing square, I know it's quite difficult at this time to get used to it, because I'm now telling you that this is the way to do it, and this is the way to do it. Again, this completing square will not appear. It is a relatively simple technique, but it is a technique you will be applying again and again and again to all the math courses you'll be taking. This quadratic equation, quadratic function, quadratic expression will never disappear in math. As long as you study math, this quadratic stuff will show up again and again. Okay? So here, it is so much easier. Look at this. You don't even need calculus here. But if you did use calculus, fine. If you take the derivative of 3c squared plus 6c plus 5, then you do get 6c plus 6, and therefore at c equals -1, the derivative is 0. But then we don't know whether that is max or min. Of course, we do know that there's a 3 here, so we know that there's a minimum. But all the things, you need so much explanation. If you do completing square, no explanation is required. You don't need any explanation here. So like I said here, look at this. If you complete this square from here to here, by the time you come here, there is nothing more to explain. See, this guy right here, it is already positive. The 3 times something squared positive plus 2, so that is what? Greater equal to 2. And then you don't need any explanation whatsoever. And there is nothing happening at the backstage. This is all front stage. Nothing working at the backstage. Those of you who are using that formula, minus x over 2b, or using this guy right here, you know what? 4. I think I forgot 4 there. But you know what? Too much formula based. You're not really understanding what's going on. You're working too much at the backstage. It's not wrong, but you know what? This kind of a method is not good. So don't you like this guy better? Look at this. It's very clean, straightforward. Again, let me tell you this one more time. Complete square is 1,000 times more important than quadratic formula. Cannot stress the importance of this guy. Any questions here? Any other questions? So let me cross it out. Okay? Again, the basic rule in math is that when you present the solution, you want to make your procedure as clear as possible using the least amount of theorems and formulas. Using the least amount of formulas and theorems. Okay? If you can avoid any kind of theorem, any kind of formula, avoid them. Also, if you can avoid, I know that this is calculus 1, and I love calculus 1 just like you do, but the rule is this. If you can avoid calculus, then avoid calculus. That's the one rule you have to learn first. You study calculus, and so the first rule you have to learn is, how can you avoid calculus? How can you do the problem without calculus? It's kind of weird, right? I'm teaching calculus, and I'm telling you to avoid calculus, but it is true. When you learn anything, the first rule is, the question is, how can you avoid that formula? After you learn a theorem, how can I avoid that formula? How can I avoid that theorem? That's really the first rule you have to learn. It's like you learn quotient rule, and then you have to learn how to avoid the quotient rule. That's the rule you have to learn for any formula or any theorem in math. It's a general rule. Okay? But just because you know calculus, it doesn't mean that you must use calculus. I think that a method which does not use calculus, many times it is actually superior. Is that clear? If you present the solution without calculus to do the same problem, then of course, personally I would consider that as a superior solution. In this case, the best solution is this, going from here to complete square. Okay, you don't need calculus. Okay, of course, you can take the derivative, and then you get 6c and then plus c, and then you do that, c is equal to -1. Yeah, it's much shorter. Yeah, sure. Okay, no, I'm saying that that's not wrong, but just do the complete square, and then that's it. There's nothing more to explain. You don't have to get into second derivative and all that max and min. It's all built in right here. Everything is happening in the front stage, so it is easy to understand. Always the best solution is the solution which is easy to understand. Easy to understand solutions are the best solutions. All right? All right, class, I almost spent an hour here. So I think this is enough. So let me just, okay, so one final call. Anybody has any more questions on anything? Now here, one thing I did not write the answer key is what? Is this, is number 7. And number 7, I just gave you the answer right here. Number 7, if you do this, the final answer comes up with this right here. This is in a general form, V, whatever your V is. Okay? But you have to do this by Riemann sum. I don't know. I'm getting the impression that many of you, you're not reading the questions correctly. I did say, what did I say on the test? I said, what did I say? It says here exactly what according to the limit sigma definition of definite integrals. How more specific do I have to write this down? And this was underlined too. According to the limit sigma definition of definite integral. In general, on the problem, now we have only one more test to go. Now, if you see the word, what is the key word here? The key word is definition. If you see this word, watch out. If you see the word definition, that means you have to now do the problem by definition. But here, I gave you a long name. According to the limit sigma definition of differential, that means you must get into this limit, and then sigma, and then that's what we call the Riemann sum, and then blah, 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 and then this is how you should have done the problem. And those of you who did not do it this way, yes, I did give you a big 0. I'm very sorry, but I think I have to be very strict here. I made it so clear to you, I cannot any make more clear than this, right? But the key word is always this word definition. So when the word definition gets in, then that means you cannot apply the rules. You have to use a definition. If I do not mention this, then you can use all the formulas you need. Except you cannot use any rules. You cannot apply any rules from calculus 2. Again, what are the rules I've seen that you cannot use? How about so? There's no L'Hopital's rule, no integration by parts, and what else? No power series, and on this test, some of you trying to do trig substitution. Now, trig substitution was okay, because if you apply trig substitution, that is not a theorem. You are actually applying a technique. Applying a technique from calculus 3 is fine, but you are not allowed to use any theorems. Applying a technique or a procedure is okay. But applying a theorem, that is not fair. Okay? So those are not allowed. So basically, by the way, even if you can apply any technique from calculus 2, in this course, you don't need those techniques, because we didn't learn that. And the techniques which we apply, with which we learn in calculus 1, are actually superior. Okay? So the method, again, if you have a method where you can use calculus 1 or calculus 2, then the calculus 1 method, I would say it is superior. It's easier to understand. Okay? It's easier to understand, so you should stay with part 1. Okay, any other questions on this test? Yeah, any questions here? Okay. Then now what I'd like to do is now let me get into section of 5.1. Oops. Annotate, let me clear all this. Okay, so that's that. So now let me move on to section 5.1. Where are we? 5.1. Where are we here? Section 5.1. 5.1? 5.1. Well, 5.1 and 5.1 solution. Okay, let's look at 5.1 first. Okay, so why don't we now cover the topic of area? Now, this topic was somewhat covered in chapter 4, but now we get into this more detail. Okay, so now here all this here. So by dx slices, now the hard part of this area on this section is that the two ways of slicing it. This is by dx slice, and this is by dy slice. You know what? I've all these formulas here, but instead of going through all these formulas here, why don't we just get into the problem specific, okay? So let's do this. Example 1. Let's look at this. So what I'm going to do is I'm going to clear all this. Let's get to example 1. So what is example 1? Let's see. Example 1 is this. Example 1, find the total area bounded by y equals x squared minus 2x and the n y equals 0. Y equals 0, which is the x-axis. So if you graph this now, what do we have? If we graph this, we get this. Oh, you know what? Okay, so let me just use black. This is xy, and let's graph this guy. Y equals x squared minus 2, or this is obviously equal to x times x minus 2, has two x-intercepts, and this is quadratic. So all of us, we know how the graph looks like. The graph is going to look like this at 0, 0, and here is a point 2, and looks like the graph is going to go like this. Now, when it comes to these kind of problems here, when it comes to these kind of problems, or area problems, or volume problems, or any kind of applied problems, is the graph required? Graph required? Graph required? Question mark? Yes or no? No.
I did that a
But
long time ago.
graph will
I'm going to read
give
that
us
before I meet with you. I got another control, okay? I just need
information we need. We need what kind of information? One kind you need, such as this graph, this graph of this what? This graph of what? This graph of quadratic. The graph of this quadratic function. Quadratic what? Quadratic function. Function what? Lies below y equals 0 for the x-axis when what? When 0 is less than x is less than 2. Or equals not 1, 0. 0 is less or equal to x is less than 2. So when you graph this, the graph will tell us quickly whether the graph is below the x-axis or above the x-axis, or when you're dealing with two curves, whether one curve is above or below the other curve, or is it to the right or left, those kind of things. So when you graph, all this information will come much quicker. Otherwise, you have to check these information algebraically, which is more work. So therefore, graph is not required. And later on, when you get good at this, you don't need to graph. Okay, you can just visualize. But the graph definitely will give us lots of information we need. So now let's see what we have. What is the total area? The total area is basically this. We chop it up like this. And then what we want to do is, yes, I did not write the detailed formula here. Okay, I see. Okay, but anyway, the area actually comes up with like this. Area. So let me write this here. So what is this? Area. This actually right here, this area is really this. Area is equal to what? The limit sigma. Let me just briefly explain to you what the formula is. And then what? Note that this function right here, we have this function. And, previously we had this function, f at x sub I, x sub k, and then delta x. This is what we had, right? But the delta x is fine. But this f at x sub k, this right here, what this really should be is this should really be height. So let me call this the height of x sub k. So replacing this f of x sub k, which is a function value, we can actually call this guy the height of the rectangle. So the area formula is basically what? The area formula is equal to base times bunch of heights. And the height, we want this to be positive. And in this case, this is the upper boundary function. Now see class, if we chop this up like this, we chop it up like this here. We chop it, and then look at this rectangle here. And why don't we look at the top of the rectangle? The top of the rectangle is over here. The top of the rectangle is over here. Let me mark with this red. And then the bottom of the rectangle is, let me mark this in green. Is over here. And then, if you now collect all the points on the top of the rectangle, and if I connect all the ones on top, all the points on top, we get this. And then, if I connect all the points on the bottom, then we get this right here. This green right here is what I call the lower boundary function. The green is called the what? Is called the lower boundary function. Because the lower boundary function is the collection of all the bottoms of the rectangle. If you collect all the tops of the rectangle, then that we get this red curve, And in this case, that's y. That's the y equals 0, the x-axis. And that red line is the red curve is what I call the upper boundary function. So what is the area going to be? The area is going to be this. The area is going to be, let me write this down. The area is going to be, what is it? Area, let me change the black. Area is equal to integral, and then eventually this limit sigma, and then this delta x right here, they get converted to integral, and then dx. In this case, dx slicing. And now, what is the upper boundary function? The upper boundary function is actually red. That's actually 0. And then minus the lower boundary function. What is the lower boundary function? The lower boundary function is right here, x squared minus 2x. That's the lower boundary function. So it is always the upper boundary function minus the lower boundary function. And then we integrate this. Of course, the area in question is this guy right here. Is this guy right here. This is the only boundary region. That is the finite region. This region right here and this region right here, they're also bounded by the curve and the line. However, the regions right here, they are unbounded regions. Unbounded regions, of course, the area will be infinity. So we are not going to deal with those kind of regions here. The region is the area is infinity, so it's not interesting. So we only in this class or in general, when on all of these kind of problems, we deal with bounded regions. Bounded regions. Regions which are kind of finite, which are not infinitely long. Actually, infinitely long regions, you will deal with those kind of things when you go to Calc 2. Again, when you go to Calc 2, you will deal with infinite regions. You will. Okay. So that's the topic when you get to Calc 2. So in this case, and then the integral, of course, is from 0 to 2. And we want to go from low to high. So from 0 to 2, not from 2 to 0, but from 0 to 2. So that's how it goes. Anybody has any questions on this? So let me save this. Let me clear this. Okay, now example 2, now we get to this. Example 3, now let me change my gear. Let me now change it to my other file, which has solutions. So let me now open up 5.1 solution file. Did I really write all the solutions here? I think I did this last week. So let me see, what did I do? Yes, I did write like this. Oh yes, I did. I wrote down all the details you need to know here. So here, let me do this. Annotate, let me clear all this. So if you look at example 1, find the total area bounded by y plus x squared this. And so the only thing which you don't see here is actually what? Is actually the graph. And the graph, I already graphed it previously. It's this graph right here. This graph right here, and this is 0 to 2. And the question is this area right here. So now in this case, let me write this in red. Red is the upper boundary curve right here. And the green is what I call the lower boundary curve. So what is the lower boundary? What is the upper boundary? What do I exactly mean by that? Well, what that really means is when you look at a rectangle right here, the red curve is the collection of all the top points of the rectangle. And then if you collect all the bottom of the rectangle, then that's the green. So if you have a tiny rectangle over here, again, the top is red, the bottom is green. So that's one by that. So if you observation, so again in example 1, observation graph, identify the region. So you always have to identify the region. That's the first step. You must identify the region. You have to understand what the region is. And then when does the graph lie above y equals 0, below at y equals 0? So you have, those are the kind of things you can get from the graph. And now, so the region lies on the difference from 0 to 2. The upper boundary curve is y equals 0, and the lower boundary curve is y equals this right here. And now the area is equal to, and then now we have this d. By the way, here which I didn't write is actually by dy slicing. Dy slicing. The two ways of slicing. We have dx slicing and dy slicing. Well, right now we only have dx, so dx slicing. And then what? And then the upper boundary curve is y plus f of x. This guy is y plus f of x. So in this case, this guy is our f of x. So this guy is our upper boundary. So this is what I mean by f of x. It happens to be the zero function. And then the other guy, this guy right here, is the lower boundary. Oh yeah, so this is our g of x. Anyway, you know what? This f of x and g of x is kind of irrelevant. They're not standard. You can call it by any name. So this one, I think I should just call this by the upper boundary, like u or something, and the lower boundary, L for lower boundary or something. Maybe that's a better way. That's a more descriptive way. And then that's into right there. All you have to is evaluate this. That's it. You get this forward 3. And of course, after you get the answer, what do? You always look at this and then try to what? Try to estimate whether this makes sense. So if you look at this here, let me see. If I, let's say, shade this region right here, if I shade this region, now how big is this area? Now this minimum right here happens to be at -1. So in this case, let's see. If I use, let's say, orange color, what is the area of this block? Area of this block. This is 2 right here. That area of that red rectangle is 1 by 2, is 2. And then the area, the shader area in black, that's the area in question. So we got 4/3, which is more than a half, and that makes sense. A little bit more than a half makes sense because this is the area. The rectangle area is 2, and looks like the area in the color in black is what? It's actually more than half. So more than half and less than 2. More than 1, and then less than 2. So about 1.4 Yeah, that makes sense.
Where does that -1/3 come from in the second to last part?
This guy right here, because you have to evaluate this guy right here. But using the fundamental theorem calculus, we just evaluate this guy. So what is the antiderivative of minus x squared? What is the antiderivative of minus x cubed? Minus x squared. The antiderivative of minus x squared is what? What is the antiderivative of minus x squared? And that will be minus 1/3 x cubed. Get this. And that's where that guy's coming from. And in order to apply the fundamental theorem calculus part 2, the plus c can be any number, so I let that be 0. So there is no need for you to put the plus c there. You can put, if you want to, you can put a plus 5, plus 10. You try any number you want, and then you end up getting the same number at the end. So it doesn't really matter. So that plus c, you have plus c here, is the best thing to do is just choose a number, and the best number for c is actually 0. So we just let that c be 0. That is, if we have to find, when you apply the fundamental calculus part 2, where we evaluate the definite interval and we need an antiderivative, we just need one antiderivative. We don't need the whole family. So, okay. Again, please review your fundamental theorem calculus really well. I think most students, you kind of know what the theorem is. You kind of know, but not exactly know. So this is the problem with many students. Many students, they kind of know, but don't exactly know what it is. So please, don't say you know it. Make sure you know it really well. Know it well. Don't just kind of know it. So that's the danger here. So here, again, in this case, a definite interval from 0 to 2 minus x squared plus 2x, and then to integrate minus x squared plus 2x, so we end up getting minus 1/3 x cubed, and then plus x squared. And this evaluating this notation right here, we have, this is also a linear operator. All the constants can come out. The plus can be separated, and this is actually how we evaluate. Otherwise, we would be writing this one negative 1/3 x cubed, and then what, plus x squared, and then what, and then this, and then evaluate this from 0 to 2. Actually, in this case, you can just do it this way. Why? Because when you plug in 0, the whole thing will be 0 anyway. So if you write it like this, that's okay. And then plug in number 2 in there, then we get minus 8/3 and then plus 4, and so that's exactly what you get. And then you get the number 4/3. And then, of course, after you get the answer, I want you to estimate. Check whether that area makes sense. Because area is a tangible thing. We know exactly how big the area should be. In our case, the area should be between 1 and 2. Between 1 and 2, but closer to 2. From the diagram, that's what we see. Okay, all right? So let me now clear all this. Oh, now, should I save it? Okay, I'll save it. Now clear all this. Now what I would like to show is maybe this is my chance to get to Desmos. So let me show you how this thing works here. So Desmos here, what is this? Desmos, where are you? Where are you here? Oh, Desmos, yeah, I'm here. Am I showing Desmos? Yes, I'm showing Desmos. Okay. So what I do is this. Let me unclick all of this. So let's say f of x is equal to what? X squared minus 2. Or minus 2x, okay, fine. And then we have, what? The y is equal to 0. The h of x, or should I just call this guy g of x? Let me call this, is it the opposite? Anyway, I guess the f and the g are opposite here. So in this case, what I'd like to do is, how about now, let me change this. So we have this curve and we have this curve. Oh, no. G of y equals 0, sorry, g of x equals 0. And so if I magnify this, we get this right here. So now you can see what area are we talking about. So we are obviously talking about this tiny area here, and so what we want to do is, the upper boundary function is what? Is 0. So we can actually call this guy by z0, or you can actually call this by what? By g of x. Our g of x is the upper boundary function, and our f of x is the lower boundary function here, f, and then we get this, x. This should be y. Good, nice picture here. So class, do you like my picture? Do you like my diagram? And so it shows where the thing is, right? Yeah, that's how it is. If I switch the opposite, if I switch the f and the g, what do you think will happen? Class, if I switch the f and the g, what will happen here? They switch the g and switch the f. The calculator will show everything. And so we get this right here, see? So the black region is the region where f of x is the upper boundary, and g of x is the lower boundary. In our case, f of x is x squared minus 2x, and g of x equals 0. That's the x-axis, y equals 0. And so for the purple portion, the upper boundary is y equals g of x. The lower boundary is y equals f of x. For the black region, the upper boundary is y equals f of x, and the lower boundary is y equals g of x. Okay? And actually, there's a way to compute this area too. This Desmos actually allows to compute the area, but anyway, that is not something I need to do here. Well, you can, but if you do that, then you will actually get the answer decimal. Okay? So, yeah, you'll get the answer decimal. I don't think you'll get the answer fraction. Once again, you cannot prove anything or get the answer by graphing. Okay, that is the rule. Again, you cannot get the answer. You cannot prove anything by this. All the details have to be done algebraically. Any questions here? Let me see. Yeah, now let's look at, how about if you now look up example 2. Example 2, now let me change it here. Example 2 is this. Example 2 is y is equal to what? Y is equal to, let me now change this. Again, let me do example 2 while I'm here. So that will be x cubed, and then x cubed plus, okay, so let me write cube here. X cubed, this is x cubed plus 2x squared, plus 2x squared, and 2x squared, and then minus 3x. The class? If you want to use you apply a graphing utility to graph this, can you? Wait a minute, what is the graph? 0 to 1? Where's the graph? Oh, the graph is over here. I see. Okay, we have this. Okay. So let's look at this. So f(x) is this, and g of x is 0, let's say. So I assigned a name. This is example 2, by the way. Example 2, since I'm at show you what is happening in example 2. So we have the two equations, the two graphs, two functions. F of y equals f of x, and that's the first function. Second function is y equals 0, which is the x-axis. So f of x is that, and then g of x is this right here. So now, what is the area in question here? What is the area in question? Oh, so, see, can I magnify this a little more? Yes, I can see, we can see the graph better. We have this graph right here. So now, can you see the graph? What area are you talking about? Now, when x is bigger than 1, we are far on the right side. It's an unbounded region. So that region we don't count. So this region here, so what is this here? So this region right here, we're not going to count. So this region, it's an unbounded region. So let me write this, unbounded region. So we do not consider unbounded region in this class. Unbounded region. And so this side right here is also an unbounded region, the bottom left. This is unbounded region too. Unbounded region. Now that unbounded region is bordered by our function and by the x-axis, or y equals 0. So it is a region bounded by those two curves, but the region is unbounded. So therefore, those kind of regions we are not going to consider in this class. Again, when you go to Calc 2, you will deal with unbounded regions. In this class, we didn't have time to cover those. That's why we didn't do it. Now, these unbounded regions, of course, the area will be infinity. So in this case, it is not of interest to us. It is infinity. Now, so this region right here is what we call the bounded region. And this, of course, the tiny region right here is a bounded region too. This region right here. So let me write this down. This down is bounded region. Okay, bounded region right here. It's very tiny, so I cannot even type it in there. But anyway, that's the bounded region, and that's the bounded region right here. So now, how about if I click at part number 4 and number 5, inequalities? Let's see what we get. We get this. So which area do you think is the question? Do you find out the region? How do you find the total area? So what area are we asking for? It says here, find the total area. Find the total area. No, when they ask for the area, what they mean is by total area. So find the total area bounded by these two functions, and they are this region 1 here, this region in black, and the region in purple, but not the big ones, not the unbounded region, but the bounded region. Now note that if you look at the bounded region here, what we do see is that this is the black curve right here. This is the what? This is the upper boundary. So that's the upper boundary. Now for the region on the right, this is the upper boundary. So let me put a mark that in orange. So orange is the upper boundary. And then now let me use green here. Green is the lower boundary here. But the green curve right here is actually the lower boundary is actually over here. So my green is the lower boundary, and orange is the upper boundary. So how do I know that that's the upper boundary, the lower boundary? Well, basically, if I let's say draw a rectangle like this, you know what? If I just draw a rectangle here, let me just draw this rectangle. Again, I don't know exactly how to draw this on decimals. So if you just draw a rectangle like this, a very thin rectangle, as you can see, then this is a thin rectangle. And then what is it? The top is on the orange curve, and the bottom is in the green curve. And on this side here, again, same thing. The top is on the orange curve, and the bottom is on the green curve. So we can see that the orange curve is what we call the upper boundary, and the green is what we call the lower boundary. So that we can make the height always positive. There's always high is up, the top minus the bottom. When you get the area by dx slicing, by the way, this is what I call the dx slicing. This is how we do it. Okay. So now I think think is so much is I think good enough here. So or should I just get the area? You know what? Maybe I'll just get the area. Area is equal to, in this case, okay, how about if I just write the area? What is this? Area of this region is equal to now. This is now divided into two pieces. Total area is actually divided into A1 plus A2. So let me write A1 plus A2. A1 is this big area right here. So let me call this guy A1. And the A2 is over here. We call this guy, how about if I call this guy A2? A2 is this region right here. A2. So what is A1? A1 is actually equal to integral from where to where? We're always going to go from low to high. So that will be from -3 to 0. And then the argument, that is the integrand, the function under the integral must be the height. And height, we want this to be low, want to be a positive quantity. So we take the upper boundary function minus the lower boundary function. What is the upper boundary? Upper boundary is this guy right here. This is what we call the upper boundary function. No, cannot call this the upper boundary. This is the upper boundary only on the interval from -3 to 0. From 0 to 1, the upper boundary and the lower boundary, they change. So for A1, the upper boundary is what? Is f of x. This guy's actually f of x. And then f of x. And then fx, and then minus g of x is the lower boundary function. In this case, the g of x is 0, so we don't need this guy. But anyway, let me just write it. And then dx. And then plus, now what is A2? When it comes to A2, now we integrate this from where to where? From 0 to 1. And then now what is the height? The height is the upper boundary minus the lower boundary. Now the upper boundary is actually the 0. 0 is which is g of x, which is 0 in our case. And then what? Minus df, minus f. Anyway, now, I don't have too much space here, so I'll just write dx here, okay? f of x dx. So that's how we get the area. So you can kind of, get the idea. Otherwise, you have to actually solve it. Okay, so now here, what I'm going to do is, let me save this. Let me go back to what we have there, okay? So let me go back to the regular files. All right, so now let's look at example 2. Example 2. There you go. Example 2, find the area bounded by y plus x cubed plus 2x squared minus 3x and y plus 0. We just did this problem on test 1. And then up to OBS stands for observation. So what is observation? Observation is a step which is not required. It is not part of the solution. But observation is a step which will help us to understand the problem. Okay? So what is observation? Do you need to the question is, do you need to make an observation? Yes, you do. What is the observation here? So let me write this down. Observation is OBS, like OBS. Observation is the observation step. Observation step. This is the what? This is a step. This is a step for what? This is for what? For what? For information and understanding the problem. That and also especially at this step, the graphing is recommended. Again, when you get good at this, later on you don't need a graph. The graph is actually going to tell us and give us a lot of information. Okay, so that's why I think most of you, I think all of you, you should probably graph it. When I ask you to graph it, you don't need to have an exact graph, but you just give me a sketch. Okay, so now let's look at the solution here. So again, factor and graph to identify the region. Basically, the biggest step, the biggest purpose of this observation is to identify the region. You have to first identify what region we are talking about. What is the region? Where does it lie? Where are the endpoints? Things like that. So when this, okay, so now we have solution, y equals this guy right here. What is that? This end, we have this right here. So we can see that the graph, this y with this cubic polynomial, the cubic polynomial, the graph is going to look like this. And we have point 1 here, and 0 here, and -3 here. So we can see that the graph is actually going to go like that, and like that, and like that. The leading coefficient is 1. That means ultimately it has to go up. So we know that the area is over here, and it's over here. And this is -3, and the 0 and 1, yes, that's what we saw on the graph. So now we have to find the area of the two regions and add them up. So from -3 to 0, -3 to 0, what is it? This upper boundary curve will be this. That will be the upper boundary. The lower boundary will be y equals 0. And when on the interval from 0 to 1, when x is between 0 and 1, upper boundary is y equals 0. The lower boundary is y equals this guy right here. And so now area, what is the area? Area is equal to interval from -3 to 0. It's the upper boundary function minus the lower boundary. Oops, I made a mistake. This should be a plus. So let me write this down. I need to make this correction. Example 2, solution, a mistake. Okay, so that's that, and then and then you get that, and then all you have to do is evaluate that. Well, I didn't finish that, but you can evaluate. Okay. Anybody has any question on this? Anybody has any questions on example 2? Easy enough? ¿Entiende? Capiche? Yes?
Peace.
Okay. Okay, so now let's save. Do I need to save this? There's nothing to save here, right? All I did was underline a bunch of stuff. Do I still need to save this page? The screen? Okay, I'll just save it. There's not much to save on this section, right? So let me just save it. And then evaluate that. Now let's move on to example 3. And example 3 is kind of interesting because now we will get into the two directions of slicing. Okay? So let's look at this. Example 3, find the area bounded by y equals 1/3 x and y equals the square root of x. Of course, when you go to decimals, you can graph those two, and then you can easily get the intersection. But here, of course, we only do things officially. Everything must be done algebraically. So here, the first thing, let's graph it and try to understand what this region is. So annotate, let me see, annotate. So here, the region is going to be like this. This is the graph right here. Things are happening in the first quadrant, so I only need to draw the first quadrant. And the graph is this one line, or what is this? 1/3 x. The 1/3 x is going to look like this. That's about 1/3 x. That's about y equals 1/3 x. And how about the graph y is equal to x squared is going to look like this. Read this again. That's how you're going to do it. This guy is going to be y equals square root of x. Y equals square root of x, and this guy is y equals 1/3 x. Okay, so we have this. So now we identify that this point right here is 9, 3. That means this point right here is 9. And this point, the y value here is what? Is 3. This guy is 3. So this point is 9, 3. And of course, the other endpoint is the origin. So that's not hard to see. So when you actually graph, when you go to the graphing utility, then these kind of things you can do it fast. But you still want to find intersections algebraically. So in this case, which lies above or what? Intersection of 0, 9, 3. How to find that? Well, this is what you do. To find intersection, so let me write it over here. To find intersection. To find the intersection of the two curves, what do you do? What do you have to left? 1/3 x. Now I cannot type it anymore. Basically you have to say 1/3 x. 1/3 x is equal to square root of x. So now I want to multiply both sides by 3. So we end up getting x is equal to what? X is equal to what? 3 square root of x. Now, if you square both sides, let me put a square here. Square both sides. X squared is equal to 9x. So either x equals 0. So from here, what we see is that x equals 0. So from here, x equals 0 or x equals 9. And if x equals 0, what is the point? The point is 0, 0. And if x equals 9, the point is 9, 3. I also want to write down the points as well. So those are the endpoints, and you can find those endpoints algebraically. Okay? By the way, on the test, you should find those points algebraically. The graphical methods are usually not accepted. Okay, so I want you to find those intersections algebraically. So 0, 0, and 9, 3. So now, let's go by dx slices. Let's see how it works. So in this case, we have what? In this case, what we do is now let's chop it up. Let's chop it up this way. Let's chop it up. Let's see. Okay, so let me chop it up over here. So chop it up over here. Now the top rectangle. This is not. We are doing dx slices. The top of the rectangle. I'm going to mark this in what? In red. Actually, I should mark it right here at the right end. I'll try to just mark on the right end. So that's the top of the rectangle. And then it's because we are all this time, we were using the right sum. So we need to chop it up on each interval. We just use the right endpoint. So that's the top right point. And then let me use green for the lower boundary. Read at this. And so you can see what is the top. The top. This point right here is actually what? Is actually yes. I can actually get into more detail, but I don't know whether you might want to. Whether you want to see this, guys. So you know what? How about this? Let me write this down. This is what I call x of k. And this point right here is actually x of k. X of k, comma, maybe I'll show you this once. This is square root of x of k. So at the right end point, that's the point. That's x of k, comma, square root of x of k. And the bottom point in green is what? The bottom point in green is x of k also. The x value is x of k. And then it's going to be 1/3 x of k. 1/3 times x of k. So this is what we want. This is a point on the lower boundary. So the point in green is the lower boundary point on the lower boundary function, and the red is the point on the upper boundary function. And if you connect all the top, then you get y plus square root of x. And if you connect all the bottom, then you get y plus 1/3 x. So now, what is this? What is the area? So this is the upper boundary is the y plus square root of x. The lower boundary is y plus 1/3 x. So what is the area? Area lies from 0 to 3. 0 to 9, x ranges from 0 to 9. And the important thing is that this guy right here, let me mark this guy. This dx is terribly important. The slicing direction. Right now, this is section 5.1, and in this class, we will go up to 5.2, or we may start section 5.3, but to remain in chapter 5 and all the application problems, whether you later on when you go to Calc 2, you will be studying surface area, and then you will be studying length of curves. And then when you go to Calc 3, you will get into surface 2, three-dimensional surfaces, volumes, and so on. On all of these remaining area, volume, surface area, and length, all of these kind of geometric problems, the very first thing you have to do is get clear the slicing direction. This is what I call the slicing direction. And the slicing direction is very important. The slicing direction, let me say, this is a slicing direction. The slicing direction, this is what? So let me write this in red. This is what? This is very important. Okay? Very important. Slicing direction, very important here. Okay. So when you before you actually when you set up the interval, what's the first thing you have to do? When you set up the interval, so let me say this here. When setting up the interval, the integral for area or area, volume, or whatever it is. You know what? These are the only things we cover in this class. By the way, in this class, Calc 1, we only do the easy volume. The general volume is actually covered in Calc 3. In Calc 3, you get into the general volume, okay? General shapes. Here, we only do the easy ones, okay? We don't do the general ones. And so this, what is it? What we have to do? Well, first, when setting up the integral for this here, first you have to decide on the slicing direction. Slicing direction, very important. Is it dx or dy? Or later on, for those students who will be taking Calc 3, is it or is it dz? In 3 dimensions, there's also dz as well. Okay, so or something else. Or when you take, those of you who are taking physics, is it d something? What else? A dt? Are you adding up over time, slicing over time? Let's say when you get like work, how much work are you doing? Then you actually cut the work in pieces, and then you actually slice it by time, or dt. Or it could be anything, okay? It could be anything else. Again, the slicing direction is very important. So in this case, dx slicing. By the way, some textbooks and some teachers, they will say, oh, we cut by vertical slices, horizontal slices, and all that. But you know what? All these terms, horizontal slices, vertical slices, and all those kinds, I think the way I find is it's confusing sometimes. So I like to make it absolutely clear. So my language is either dx slicing or dy slicing, or dy slices, or dx slices, or dz slices, dt slices. This is how I call them, and this is the slicing direction. Okay. In this case, these are the vertical slices, if you like. But again, the vertical slices, again, it's very confusing. Which slices are vertical slices? Some people say that this is a vertical slice, or if you call it horizontally, each piece horizontal, isn't that vertical slices too? Well, it depends how you look at it. So these horizontal slices, vertical slices, you know what? To me, they are very confusing. Okay, so I like to make it absolutely clear. So I use a language, dy slices or dx slices. Much more clear. There's no confusion whatsoever. That's what I like. I don't like confusing. I don't like confusing instructions, okay? So now we have this, and now we get this upper boundary function is y equals square root of x, and then minus 1/3 x, so we get this and that, and then there you go, and then the answer is 4.5. Any questions here? Anybody have any questions? The y plus fx is the upper boundary, and the lower bound function is y plus 1/3 x. There's always the upper boundary minus the lower boundary, so that the integrand is always positive, and then the dx must be positive. So again, the integral from 0 to 9, and then upper boundary minus lower boundary. The slicing direction is x here. And by the way, once the slicing direction is x, so basically here's the key. If dx slicing, all functions must be solved in terms of x. That means need what? Need y equals f of x and y equals g of x. That's the form we need. So all the boundary functions must be written in the form y equals fx and y equals g of x. So that everything is solved in terms of x. So this is x here. So if this is x, then that must be an x, and this must be an x, and the limits must be an x as well. So this is from x equals 0 to x equals 9, and then this is square of x, and then this is x right here. And of course, slicing direction is dx is terribly important one is this guy right here. And if you integrate this, you get in this and that, and then you can do the calculation, and we end up getting 4.5. If you look at this area here, how big of an area does this guy look like? Does this area kind of look like it's about 4.5? Well, first of all, our graph is not that accurate. So when you actually go to decimals, we can actually better. So how big is this? Is it like that big, or is it like this big, or does it come like this? Is it really skinny? I mean, is this area really skinny, or is it thick? How that we don't know. So graphing this accurately is not easy. So you can, if you go to a graphing calculator, then of course you'll get a better graph. So here we only estimate. So the question is, well, how big is this area? What we can show, what we can show is that, let's say if you look at this rectangle here, that area is this big rectangle is 3 by 9, which is 27. And our area is on top, in the top half. So what is the area of this triangle? This big triangle here. This, how about this? Let me now use orange here. Orange. Should I use orange? All right. You know what? You get this triangle here. Triangle from here to here to here. That's half of it. That area of the triangle is about 13.5. And so now our area is even less than that. So if you take about half of that 13.5, is about 7. But we are not sure how thick this guy is. In our case, what today we get 4.5. Okay, so makes sense? Yeah, makes sense. It's not 45 or minus 4. Okay, so 4.5. Okay, so kind of makes sense. All right. So we get the area. So now that is the area. So let me save this. And now what I'm going to do is I'm going to undo some of the stuff here. I'm going to make this cleaner. Okay. Now let's look at the second part, by dy slices. The question is, can we get the area by dx slices? Can you do that? Well, let's see. Let's see whether you can do this by dx slices, dy slices. So if we cut up in dy slices, that means we'll cut up this way. So the rectangle, a typical rectangle is going to be like this. Like this. That's actually going to be right here and right here. So this top here actually is going to be y sub k, and the bottom is going to be y sub k minus 1. This is y sub k. So let me write that again. This is y sub k. Y sub k over here, and this is y sub k is over here. Bottom is this. And then if you use a right end point, in this case, we don't have a right end because it's the top and bottom, so we use the top one. So this is yk. The one with the larger y value. So when you cut it to x direction, x sub k minus 1 and x sub k, of course, y sub k is the right end point, and that's the one with the highest x value. If you chop it in dy slices, the top one will be the one with highest y value. So that will be equivalent to x sub k, but now we call it y sub k. So we get this. Now, look at this structure. Now we're trying to get this rectangle right here. Now, when you get into this rectangle, that means these are dy slices. So now, let's look at the solution, second solution, by dy slices. The very first thing we have to get is this dy slices right here. dy. This is now the slicing direction. Slicing direction is now dy. Slicing direction is dy. Oops, no. Let me just write this in red. So dy. Now, if we go by dy slices, then everything must be written in terms of y. It must be solved for y. So now, in this case, now let's look at this. When we slice in dy slices, then we don't have the upper boundary or the lower boundary. What we do have is we now have, let me now write this in red. The point on this side, what is the point on this side? The point on this side is, let me see. The point on this side is, this right here, is this point right here. And that's what I call the right boundary. And then now, what is the green? This point is right here. This is what I call the left boundary. So in this case, we don't have, how about this? Maybe I'll clear this. Let me erase these 2 points right here. Let me just, I just successfully erased the blue and the green from the other rectangle. So now we have a horizontal slice. Yeah, this is a horizontal slice, but I call this a slice by dy slices. dy slices or dy slicing. The red curve is now the right boundary, and the green curve is now called the left boundary. So also everything has to be solved for y. So in this case, the equation we had here is what? The equation we have is y is equal to 1/3. Y is equal to 1/3 x. I should not write that in green, but let me mark this in red. So this is y equals 1/3 x. However, this will be changed to x equals 3y, as everything must be solved in terms of y. So we now need x equals 3y. The form of the equation must change. And then how about the green curve right here? This is y equals x squared. Now what is the lower boundary curve? The lower boundary curve is now what? We also have to solve in terms of y. Therefore, this is now going to be x is equal to y squared. X equals y squared. Actually, the curve is going to go all the way to this side as well. So in our case, we don't need this part, but this is x equals y squared. But even the top part over there, that's still y equals x